Now, first of all, we have to know what are the natural elements. Natural elements are already available like O2, H2, N2 and graphite, solid in carbon form. These are the natural elements, that is naturally occurring elements. So, since they are naturally occurring elements, no need to form them. So, we can assign the value of the enthalpy formation of these 4 elements as 0. Now, any other element if you take, that has to be formed by these 4 elements only. So, for example, CO can be formed by having some graphite and over which you can put some hot oxygen. Basically, you have to actually put graphite and oxygen in a chamber, constant pressure chamber, and try to trigger the reaction by heating it slowly. And once the sufficient heat is supplied, then the reaction between the graphite and oxygen will take place to form CO. And now cool the CO to 298 Kelvin, the heat which is released will be the enthalpy of formation of CO. Similarly, for fuel species, say CH4, C2H2, etc., we have to consider a reaction between graphite and hydrogen. Do you understand? So, all other materials can be formed using the 4 basic elements or natural elements. That is the enthalpy formation. We can also use the calculation based on bond energy to evaluate the enthalpy formation. So, there are several ways to estimate this. So, there are tabulations where for several species enthalpy of formation is available by either the careful experiments or bond energy related principles. The second term for calculating the standard enthalpy is the sensible enthalpy, which is the enthalpy associated with the temperature change. From 298 it may reach 600, 700 Kelvin. So, that is called sensible enthalpy, which is the increase in the enthalpy due to increase in temperature from 298 to the value of T. So, now coming back to the equation, I write for the methane combustion, I write the heat release rate equal to the enthalpy of the products minus the enthalpy of the reactant. Now, standard enthalpy of formation, okay, now for simplicity I have removed the superscript 0, because we know that for standard enthalpy we have already used the atmospheric pressure conditions. So, for standard heat of reaction, the temperature of the reactants are at 298, products are also cooled 298. So, the temperatures TR and TP are both at 298 Kelvin, that is the reference temperature itself. That means there is no sensible enthalpy for these cases. So, Q dot will be equal to HF CO2 plus 2HF H2O plus 7.52 HFN2 minus HFCH4 minus 2 HFO2 minus 7.52 HFN2. But please see that N2, O2 are basic elements. That means it doesn't have a enthalpy formation. That is, its enthalpy formation value is 0. So, we can eliminate those terms and write Q dot equal to HFCO2 plus 2 HFH2O minus the enthalpy formation of the methane. So, this is the equation. So, if you go to NIST database, NIST website, you can see the huge database there, from which we can get these values. As I told you, tabulation of these values are available. From these values, I substitute the value for the enthalpy of formation of CO2 is 393.52 kilojoule per mole. or megajoule per kilomole minus 2 times enthalpy formation of water vapor is minus 241.83 minus enthalpy formation of methane is minus 74.5. So, when you do this, the standard heat of reaction for methane is obtained as minus 802.68 kilojoule per mole of methane. Why I say mole of methane specifically is because this reaction is written per mole of methane. Okay, the global reaction is written per mole of methane. Based upon this reaction only, the first law is written. Correct? The number of moles of products, etc., depend upon the number of kilomoles of methane used. Here, number of kilomoles of methane is 1. So, the reaction is written per kilomole of methane. So, the heat of reaction, standard heat of reaction is calculated per kilomole of methane, kilojoule per mole of methane in this case. Okay. So, methane reaction is exothermic reaction. Obviously, we have seen that the value comes out to be negative because it is an exothermic reaction, heat is released and heat comes out to the surroundings. Surrounding, there is a heat gain, but the sign convention in thermodynamics is heat supplied to the control volume is positive, heat rejected from the control volume is negative. So, heat engine's sign convention. So, standard heat of reaction of methane is negative because heat is released from the control volume to the surroundings. And one more thing is we have written is per kilomole of methane or per mole of methane because the reaction is written in that manner. I can first convert this to per kg of methane, correct? So, what I do that, so first of all what I do is mole to kilomole I convert, that is minus 802.68 into 1000 kilojoule per kilomole divided by the molecular weight. This is the molecular weight of methane. Okay, when I do that, I get 50.2 megajoules of heat released, or heat standard heat of reaction is minus 50.2 megajoules per kg of methane. So, 802.68 is kilojoule per mole of methane. Now, minus 50.2 is megajoules per kg of methane. Okay, now heat of reaction is negative. On the other hand, standard heat of combustion is the negative of the heat of reaction. That is what the surroundings receive. That is the standard heat of combustion, which is the heating value or the calorific value. Okay, just say minus of heat of reaction. That is, I will say delta H reaction will be equal to minus delta H combustion, which is equal to calorific value. Okay, so the heating value of methane is 50.2 megajoule per kilogram of methane, positive. Now, this is heating value and calorific value are the same, but there is one important thing we have to consider here. Is this a lower heating value or a higher heating value? What do you mean by lower and higher heating value? Comes in because of the fact that there is H2O in the product. H2O is a condensable vapor. So, based upon temperature, so also we are cooling it to 298 Kelvin. So, that means there will be condensation. But it is based upon the vapor pressure or the partial pressure of water vapor. amount of condensation will occur. That means we cannot surely say that the product has water in vapor form or liquid form entirely, but we can calculate the extremes. If the water is assumed to be in the vapor form, then what you obtain from this equation is the lower calorific value, and when you try to extract the latent heat from the water and condense it to liquid, and that heat which is removed from the water vapor also is added to the heat of reaction, then I get higher calorific value. Okay, so that means when the product water is in liquid form, then I get the higher calorific value. If it is in vapor form, I get the lower calorific value. Okay, so that means the difference between the higher and lower calorific value is the latent heat of vaporization of water. Okay, now, so let us not worry about this. We can calculate both the values, and we can say that the heat release will be in between these two, lower and higher calorific values. Now, heat of reaction can also be written in terms of per mole or per kg of oxygen consumed. Okay, this is very important. So, let us take the instant of the methane combustion, where for 1 mole of methane, 2 moles of oxygen is consumed. So, I can say minus 802.68 kilojoule per mole of methane can be written as minus 802.68 divided by 2 kilojoules per mole of oxygen. So, that is what I have written here. Okay. Because of the reaction itself, CH4 plus 2O2 giving the products, correct? So, now I can now convert this into per kg of O2. How? Again same thing, mole to kilomole multiplied by 1000 divided by the molecular weight to calculate the kilomole to kg. So, I get 12.54 megajoules of heat of reaction per kg of O2. Do you understand? So, what is evident from this is I can write the heat of reaction per mole of fuel, per kg of fuel, per mole of oxygen, per kg of oxygen, or products are also formed in the same manner, correct? So, for example, if 1 kilomole of methane is burnt, 1 kilomole of CO2 is formed. So, I can also write the heat per kilomole of CO2 produced. Okay. So, let us consider one more example, say methanol, which is CH3OH. Okay. Using the same thing, but anyway, you have to use the heat of formation of methanol. I calculate the heat of combustion as around 20 megajoules per kilogram of methanol. When I do that, so when I write this equation, it will be 1.5 times O2 plus 3.76 N2 giving products. So, now per mole of methanol, I will consume 1.5 moles of oxygen. So, using that, and I can use the same procedure here and get 13.3 megajoules of heat release per kg of O2 consumed in the methanol combustion. Okay. So, you can see that the range is for methane I got 12.5 and for methanol I am getting 13.3. For several fuels, if the same procedure is repeated, we will see that the heat of combustion per kg of oxygen will be in this range, 13.1 plus or minus 0.7 megajoules per kg of O2. So, this small range of the heat released for per kg of oxygen irrespective of various fuels, is the concept used in the oxygen calorimetry. That means if you know how much oxygen has been consumed, then we can find the heat release. Just take the value as 13.1 megajoule per kg of oxygen and multiply this 13.1 megajoules with the oxygen which is consumed. That will give you the heat release rate. So, need not worry about what is the type of fuel which is used. So, now as I told you, I can write the standard heat of combustion per kilogram of CO2 produced. So, 1 mole of methane produces 1 mole of CO2. So, you use the same thing. So, 802.68 into 1000, that is to convert it to kilomole, divided by the 44 is the molecular weight of CO2. So, you get 18.2. Okay, 18.2 kilojoule megajoule, 18.2 megajoule per kg of CO2 produced. But this methane combustion is going to give you a extreme value for the heat of combustion per kg of CO2. When you consider any other fuel, say starting from pentane to pentane is C5, toluene is C12. So, if you consider this range, the heat of combustion per kg of CO2 lies between 14.7 to 14.2. So, the average value is 13.3 plus or minus 1.5. Okay. So, not only these state hydrocarbons, several hydrocarbons have been tested. So, experimental evidence is the average value of heat of combustion, standard heat of combustion per kg of CO2 produced is 13.3 plus or minus 1.5. So, you can see that these two, the pentane to toluene also is within this range, but methane is slightly out of range. Okay. So, except one or two fuels, you will see that the oxygen based calorimetry or the carbon dioxide based calorimetry works very well. In fact, the oxygen based calorimetry works well for methane also. Okay, now this is, let us consider a liquid fuel and see how to calculate the standard heat of combustion. So, stoichiometric combustion equation for N-heptane C7H16, which is the commonly used liquid fuel. For any lab tests for fires, heptane is used. So, let us take the stoichiometric equation C7H16 plus 11, that is 7 plus 16 by 4, O2 plus 3.76 N2 gives 7 times CO2, 8 times H2O plus 41.36 times N2. Okay, so this is the equation. Now, please see that this is liquid. It may be in gaseous state. I can vaporize this and use the vapor, but also I can use the liquid and supply the heat there and calculate from the enthalpy of formation of the liquid itself. So, what is the difference? Standard enthalpy formation of N-heptane in gaseous state is minus 189.3 kilojoule per mole. For liquid it is minus 225.9. Okay, liquid, because you have to add some heat to this to get it to the vapor state. So, based upon whether the fuel is in liquid or vapor state, I will get the appropriate value of enthalpy formation to be used in the reaction equation to calculate the heat of reaction. Okay. So, basically what happens is I have to have, I can draw a simple diagram. H versus temperature, basically it goes like this. So, these two lines represent reactants and these two lines represent products, and here this is the enthalpy. For example, when the reactant has fuel in vapor form, this is the enthalpy for the same temperature I am saying, when the fuel is in liquid form. Similarly, here some product is formed at some particular temperature where the product is in vapor form and it is in liquid form. So, do you understand? So, there are variations. When there is a condensable or evaporatable substance present, then the enthalpy of formation of a particular component should be used properly. That is, whether the liquid phase is existing or gas phase is present. So, for example, if liquid fuel is used, the enthalpy of formation of liquid should be used. When the water vapor is condensed to liquid, then enthalpy of formation of liquid water should be used in the product side. Okay, that's what is very important. So, based upon this, the heat of reaction, others there is no change in other say CO2, H2, etc. Correct. So, only for the fuel which can be in liquid state or water which can be in liquid or vapor state, you need to appropriately choose the enthalpy of formation. So, now on mass basis, the heat of reaction of vapor heptane can be got as minus 45,000 kilojoule per kg of fuel. Here the water is in vapor state. So, I am coming from the vapor state reactant to water which is also in vapor state. This is 45. So, this is called lower calorific value. When N-heptane is in liquid state initially, you will get a slightly lesser value. That is, instead of 45 megajoules per kilogram of heptane, I will get 44.6 megajoules per kilogram of heptane. Okay, now when you have a liquid fuel and liquid water, then you get the maximum heat release. Okay, so standard heat of combustion is obtained when the reactant enter and product leave at standard conditions of 1 atmosphere and 298. But there are situations that is only for finding the calorific, theoretical calorific value. Standard heat of combustion is used. But in practice, the products may leave at higher temperature. Correct. When there is a smoke in a compartment, through some ventilation, products can leave at a higher temperature. Okay. Now, let us consider an example in which heptane is burning and there is a good air supply. Say, let us say the air which is coming in is 125% of stoichiometric air. So, the combustion reaction for this is written as C7H16 plus 13.75 O2 plus 3.76 N2 giving. Again, I am saying that there is no dissociation. So, 7 CO2 plus 8 H2O plus excess oxygen. See, C7H16 requires 11 O2. Now, 13.75 O2 is fed. So, 2.75 O2 is seen in the product side. So, now reactants are entering at 298, but products are leaving at 1200 Kelvin, typically as in from a compartment fire and so on. So, how will you calculate the heat of reaction here? Please understand, this is not standard heat of reaction. Standard heat of reaction requires the products to be cooled to 298 Kelvin. So, here Q dot is the heat which is released when the products leave at 1200 Kelvin. Okay. Obviously, it will be less than the standard heat of reaction. So, here I am writing the product side, 7 kilomoles of CO2 per second. This is enthalpy of formation of CO2 plus this is sensible enthalpy. Okay. Again, there are correlations or tables from which I can get this value. Similarly, 8 times for H2O, this is the enthalpy formation of H2O plus sensible enthalpy which is obtained from the table corresponding to 1200 Kelvin plus 2.75 O2. O2 does not have enthalpy formation, so only enthalpy, sensible enthalpy is included here. Similarly, for the nitrogen, sensible enthalpy is included. Minus what is this 189.3? That will be the enthalpy of formation of C7H16. Because reactants are entering at 298, so in the reactant side, enthalpy of formation of O2 and N2 are 0. Only for heptane, I am considering this value. Vapor, we already displayed this. Vapor's enthalpy formation is minus 189.3. So, I have considered here. If it is liquid which is entering, we have to consider the enthalpy formation of liquid. Okay. So, now as I told you, to evaluate the sensible enthalpy, I can use the NIST database where polynomials of Cp will be written given as a function of temperature in a given range. For example, it may start from 298 to 1000, 1000 to 2000, etc. So, it is a piecewise polynomial where it is dependent on temperature, but temperature some normalization is done here. For example, T star equal to T by 1000 and the value of A, B, C, D, E, etc. are available in the database itself, and for CO2 I have just listed the values, typical values from the same database. So, once you do this integration, I will get the sensible enthalpy, then use that in the calculation, or you can use tables. In some cases, direct tables are available from which corresponding to the temperature of 1200 Kelvin, you can take the sensible enthalpy for CO2 like 44.47 or H2O it is 34.51 etc. and calculate this. Now, you get the heat of reaction as minus 2377.65 kilojoule per mole of C7H16. But this is not connected with the standard heat. Okay, please understand that. Okay. So, what you have done here is basically considering when you calculate the enthalpy of a species at a given temperature, I have used enthalpy formation of the species at 298 Kelvin, okay, plus the sensible enthalpy at a particular temperature. So, that is what I have illustrated in this. For the delta H, I can use either the polynomials or some table listed values. So, obviously, this will be lesser than this, what you calculate here is lesser than what we calculated using the standard conditions. Like when you cool it more and more, you can extract more and more heat. So, maximum heat which is released is got when the reactant enter at the standard state of 298, products are formed and they are also cooled to 298. Now, heat calculation for multi-component fuel. Typical example is for the LPG, the same composition which we have considered in the stoichiometric reaction when we wrote that, the same thing we consider here. Okay. Now, these are all the percentages by volume. So, the volume fractions, when I divide this percentage by 100, I get the volume fraction which is same as the mole fraction. Okay. So, for example, for the propane, the mole fraction will be 0.1331 because propane, sorry, no, it is not propane, it is about 13.31 C3H8 is present. So, 13.31 by 100 will be the volume fraction which is same as the mole fraction for the propane. Now, in order to do this, we need, it's a mixture. So, we need to apply some mixing rules. So, basically I find the molecular weight for this. Molecular weight of LPG will be equal to mole fraction of each component in this mixture of LPG into the corresponding molecular weight of the species. Okay. So, for example, for if it is for propane, I will say 0.1331 into molecular weight of propane, that is 3 into 12 plus 8. So, I will put this. and add all this to get the molecular weight of LPG, which is calculated as 54.2 kilogram per kilomole. So it is heavier than air. We have already seen this. So now standard enthalpy of formation of LPG you have to calculate, because all these components has enthalpy of formation. Okay, that also in molar basis. When you say molar basis per mole, I can use a simple mixing rule based upon mole fraction. This is mole fraction. So mole fraction of a particular component into the enthalpy of formation of the particular component, that you sum up for all the components. Say for example, there are about 15 components, you just add them, then you will get the enthalpy of formation of LPG. Okay, so enthalpy formation of LPG is got. Then if, okay, now before going to the equation, I want to mention one point here. If mass fractions are given, then we have to use the mass based specific properties and use the mixing rule what I have demonstrated before. Okay, so in order to do that, you have to divide the molar enthalpy formation of a component by its molecular mass to get the per kg specific quantity. So now mixture enthalpy of formation of or for the LPG is now got. Okay, then you can use this global equation where I have written C 3.77 H 8.98. How I get this? Just add all the, so first convert into 1 kilomole of fuel the components and add all the C atoms and H atoms. I get this formula. Note that it's not integer. Okay, plus for this, when it is burning completely, then 3.77 kilomoles of CO2 will be produced, 8.98 by 2, that is 4.49 kilomoles of H2O will be got, and what will be the, this is the stoichiometric, so all the oxygen is consumed and nitrogen is kept inert. So what is the heat of reaction for this? It will be the enthalpy of formation of the product, because it is standard heat. So products are also cooled to 298 Kelvin. So 3.77 HFCO2 plus 4.49 HFH2O minus enthalpy of formation of LPG, which is got from the mixing rule. So in order to get the enthalpy of formation, a mixing rule is particularly used. Okay, so I will stop here. I'll continue in the next class.